Hello, my name is Mika. I would like to present my paper review entitled Effect of Organic Liaison on Zinc Oxide Nanostructure and to investigate the photocatalytic activity under the visible light illumination. And this introduction, the paper discusses about pyridine passivated zinc oxide by using co-precipitation method by varying the amount of pyridine. The degradation of the rate of the metal blue in aqueous solutions under UV light radiation were used to assess the photocatalytic activity. Various parameters affecting photodegradation process, like to the sake of catalyst, morphology, dye concentration, and solution pH under visible light radiation, were studied to decide the degradation efficiency. Okay, about the synthesis procedure, I make a simple animation to make it easier of the synthesis process. In a typical experiment, there are 4 different concentration of pyridine, such as 0.4, 0.6, 0.8, and 1 milliliters of pyridine were added dropwise to the zinc acetate solutions, and the solution was stirred at room temperature. And then the 0.2 m of sodium hydroxide dropped to the above solution to reach the pH value of 12. And then the solution was left for reaction to proceed for about 10 hours. The resulting precipitate was washed several times with deionized water and ethanol, and actually it dried at 80 degrees Celsius for an hour. The obtained white powders were labeled as PZ04, PZ06, PZ08, and PZ1. Actually, we know the pre and post condition just labeled. And in the discussion from the XRD patterns of the various concentration by POS passivated zinc oxide nanostructure were recorded are all the diffraction peaks of synthesized samples so similar without any change in the relative intensities. The sharp diffraction peaks show the good crystal nature. And then from the second feature, the absorption peaks is shifted for passivated zinc oxide nanostructure compared to pure zinc oxide, as shown this figure. The pyridine molecule caps the surface of zinc oxide nanoparticles through the coordinate bond formation between the lone pair of the nitrogen of C and bond. Photoluminescence spectra for Py passivated zinc oxide nanostructure. All the samples show a broad luminescence in the visible regions, which is attributed due to the deep level defect, like surface defects and oxygen vacancy in zinc oxide. The above result apparently evident that Py molecules were efficiently passivated the surface of zinc oxide. In general, the growth of nanocrystal was influenced mainly by the reaction condition. In this work, the reaction condition was altered with the concentration of the passivating agent. From the image of the ESSEN, it is observed that the information of the nanosheet gradually getting denser with the higher concentration with zero point 0.4 until 1 milliliter of pyridine. This particle formation may be due to the hydrolysis process in the reaction. In this observed that as the concentration of pyridine matches 1 milliliters, like this picture, this nanoseed arranged to form like a hierarchical flower, like a nanostructure. From figure 6, the TEM image of the various concentration of PY phase-phase zinc oxide nanoseed. The clear crystalline fringe of the HRTEM image shows the good crystalline nature of the zinc oxide in agreement with the XRD result. In figure 7, the slight shift in the peak position is due to the interaction of zinc with the amine molecules, and all the results demonstrated above clearly evidence the presence of a high concentration of oxygen defects in the samples. In figure 8, shown N2, absorption-desorption isotherms, and a pore size distribution estimate using the Barrett-Joyner and Helanda BGH analysis. All isotherms exhibited type 4 behavior with H1 hysteresis loops, which is characteristic of zinc oxide. The surface area of the sample prepared from various PY concentrations were determined from BET analysis. The above pore size analysis revealed that the higher concentration of PY produced the pore size. This significantly suppresses the interaction of the organic pollutant with the photocatalyst. Larger concentrations of hydroxyl ions are formed at higher solution pH, which react with holes to form hydroxyl radicals and enhance the MB or metal blue photodegradation. On further increase of the pH, there is a slight decrease in photodegradation efficiency due to the hydroxyl ions, which complete with the dye molecule for surface absorption of the photocatalyst. All precipitated sample dosage was fixed to 75 mg per liter, and the pH of the solution was maintained at 11. It is evident that the degradation efficiency decreased with the increase in dye concentration. The generation of the electron holes pairs increased for the higher catalyst dosage and result in the formation of OH radical, which increases the photodegradation. The exceeding catalyst dosage reduced like penetration or reduction in the catalyst surface area due to the agglomeration of the nanoparticles. This is the photocatalyst PZ 0.6 show better specific surface area, more reactive sites, higher ability towards absorption of light. Smaller in size with high dispersion usually lead to better photodegradation efficiently. And it is such a feature that a linear relationship exhibits between learned CO over CT and irradiation time. For this table 1, it can be observed that on further increase of photocatalytic activity by introducing precipitating agent in zinc oxide lattice extend the lifetime of the charge carriers. From the summary, PY precipitated zinc oxide nanostructure processing different morphologies were synthesized through the co-precipitation method by varying the amount of PY. And the current of study is about the solution concentration. Photocatalyst reduced in pH were 10 ppm. Under optimal condition, enhanced photocatalytic activity were observed the higher concentration of pyridine. Then equilibrium time is the reduce the catalytic activity towards the dye degradation. Then absorb is promoted by pyridine catalysts dispersed in the dye solution. Thank you.